Hello students, in the last session we completed the basic understanding that is needed for the work, and then we did see what is the formula for the work. Okay, so then we did complete the dot product or the scalar product and the mathematical background that we need to know regarding the dot product. Okay, so that too was done, and finally we saw what is meant by kinetic energy and the derivation part for the kinetic energy. So those were the stuff that we actually did in the last session. So in this session we will do like the potential energy. So potential energy is actually a simple one, a small tweaking that we do to the work, we will end up getting the potential energy. That's an easy part. Then we will see how to relate between the potential and then the kinetic energy to get the total energy. The summation of those two stuff will give you the total energy. We'll see that one. So the last part that we will see in this session will be the lengthy one. So that will be like the vertical motion of a bob in a circular motion. Okay, so vertical circular motion of a bob will be the last part that we will see. So that will be the lengthier one. Okay, so we will see like three important concept in this session. Fine. So in the next sessions we will do like collisions and all those stuff. Fine. So let's jump into the theory. So here you have got like potential energy, right? So we just need to find what is meant by potential energy. So you do not want to do more derivation to get the potential energy. So generally when you do like work, so when you calculate work, what you do is like you just do the dot product between the force and then the displacement. You will end up you'll end up getting the work, right? So whenever you got like the energy to be released, that will be positive, right? So that will be positive. So generally the energy release will be interpreted in the form of like kinetic energy. Okay, so it will be obvious to us in the form of kinetic energy, right? Same way, when the work done was, when the notation you get to be in negative, it actually means the energy got stored in that particular, because of that particular force field. Okay, so that's how it's going to be, right? So when you are about to get the total energy, so total energy actually means the energy will get converted from one form to another form, right? It will not be destroyed, right? So that's the notion, right? So energy will always be conserved. Fine. So in that situation, if you get a negative sign because for the energy storage stuff, so it will become hard to add those kinetic and potential to get the total energy, right? So in order to make the energy storage to become positive, what I'll do is I'll just put extra negative sign in front of the work done to get the potential, right? So in entire physics, if I'm going to tell you potential actually means energy is getting stored in that system or in that experiment or in that in that situation. If the energy gets stored, then we'll call it as potential energy, right? So if you do like force balance, if you do like dot product between the force and the displacement, you'll end up getting the negative sign. What I will do is, just to remove that negative sign, I'll just multiply it with extra one more negative sign so that the entire term becomes positive. That's it, finished, right? So whenever they are asking you to find the potential energy, it simply means put a negative sign in front of the work done, you will end up getting the potential energy. That's it. Fine. So here, simple, straight away, potential energy U is nothing but the negative of the work done. So that I'll just nullify that negative sign and make this term positive. That's the only idea behind putting the negative sign, right? To get the positive value for the energy storage, that's it. So negative of work done will give you the potential energy. So then you do the integral. So integral of vector f dot dr or dx. So dx, if I put in like dx, it simply means the entire motion is along the x direction. If I plug in like dr, it means it could be like some component could be along the x, some component could be along the y or j, y or z, whatever it is. Okay, just to generalize the stuff, I have just plugged in dr. Okay, so even if I put in here like dx, both are just the same thing. Do not want to confuse those stuff. Okay, I'm just finding here the potential, therefore put extra negative sign in front of this integral. So this will be the formula for the potential, right? So in the case of potential, if the answer was like positive, right? So in the case of potential, if the answer was like positive, which means energy is stored. Okay, so when the energy is stored, you'll get the potential to be like positive. Okay, just to nullify that negative sign, I've just put in extra one more negative sign, and then I just told you a new term called as potential energy. Okay, fine, that's it. If the potential energy is like positive, then energy is stored. It is like other way around for the work that we have already learned in the last session. So here, if the potential energy U is negative, then it simply means the energy got released. Okay, the other way around of the work done that we have already learned. So if it is like negative, then energy is released. Okay, you should be clear with this idea, simple basic one, right? The reason why we introduced a new concept and a term called potential energy is because to find the total energy. Okay, so as I've already told you, we already know that energy will always be conserved. It will neither be created nor be destroyed. It will just get converted from one form to the other form, right? So that's what we are going to see over here. So in this situation, what I did is I just threw a ball from the surface of the earth, okay, with certain velocity v. It got projected with a velocity v, okay. At that point of throw, you got the kinetic energy to be maximum, whereas potential energy was zero because there wasn't any force, there wasn't any energy stored because of this force field, okay. As far as gravitational field is concerned, we will always study with respect to the earth's surface, right? So when it was about the point of projection, at that point the field hasn't yet started, so that was the starting point for that force field, right? With respect to the ground, even if you go beneath the earth's surface, you will still have the gravitational field. But generally for our study, for simpler case study, right, while we do the chapter gravitation, we will do all those gravitational force inside the earth and all those stuff, as if now for the generalized situation, so earth, the surface of the earth will be the starting point for that particular object and for that particular force field, right? So if that was the case, initially as this was the starting point, there wasn't any potential energy stored because that was the point of projection. Only when it starts moving against that force field, you will end up generating the potential energy that will get stored. Fine. So at the point of projection or at the point of throw, only energy that we will have will be the kinetic energy. That's going to be the maximum, right? So kinetic energy will be maximum. Okay, and obviously that will be in positive, right? Got it? Same way, at the point of throw, you will not have any potential energy stored because it hasn't pierced through that force field. Only when it starts moving against that force field, you will end up getting the energy storage, right? That's called as potential, right? So here, potential energy will be zero. Then at the maximum point, when it has reached its maximum point, obviously there wasn't any energy loss to the surrounding. If that was the case, the entire kinetic energy should get stored, like, because of this force field in terms of potential energy, right? Therefore, when it has reached the maximum position, obviously the velocity will be zero, therefore kinetic energy will become zero, where in the case of potential energy, it will reach the exact magnitude of this kinetic energy for the point of projection because the entire energy got transferred to the potential energy because of this force field, right? So here potential energy will become maximum, potential energy will become maximum, that by the way that too will be like positive, okay. So it is, now you should have understand now we should have understood the reason why we took the potential energy as a new concept, because initially the total, if I give you some value like kinetic energy was equal to 5 joule, when it has reached its topmost position where the velocity became zero, at that point the entire kinetic energy goes to zero. Same way, if you evaluate the potential energy, that will be like 5 joule and that too will be like positive. That is when I'll be able to tell total energy at all those instants were same, right? If I just stick to the notion of work, then in that situation this term will become negative, then it will become illogical to compare those two parameters, right? Therefore, in order to make all those value into a certain positive thing, I just introduced a concept of potential energy, right? It should be clear. Okay, same way, if I just take any intermediary position between the topmost point and the bottom one, you will have some quantity to be as kinetic energy and the rest all other quantity will be stored in the form of potential energy. Summation of those two stuff will again give you the total energy, which is the constant one, right? So if I take an in between intermediary position, then in that situation, okay, you will have some amount of kinetic energy left, which will be responsible for the upward motion of that particular object. Same way, some part of the velocity would have been lost. Those lost velocity will be stored because of the force field in the form of potential energy, right? It should be clear. So in the intermediary position, you will still have kinetic and then the potential energy. Potential energy, summation of those two, kinetic and potential energy, will give you the total energy at all those instants. At the topmost point, the potential energy will be equal to the total energy. In the intermediary position, summation of those two values will give you the total energy. At the starting point where it has been thrown upwards, you will only have the kinetic energy that will be equal to the total energy, right? So total energy at all those instants were like same. Okay, it is nothing but the summation of potential energy and then the kinetic energy. That's it, finished. Okay, so total energy will is nothing but the summation of potential energy. Okay, we have made it positive, right? For the energy storage we have made it positive, therefore I can add it. Potential energy will be represented, will be designated by the letter U, capital U. Okay, so whenever I tell you like capital U, it actually means the potential energy. It will be the summation of potential energy and kinetic energy. Okay, so this will be designated by K or KE, whatever it is. Okay, so this will be represented by the letter K. So this is what you need to know regarding the total energy. It is the summation of potential and then the kinetic energy, right? So now like two concepts are done, which is like potential energy and then the total energy. Now we are moving into the larger part of the session. Yeah, this will be really big. Okay, so here you consider a string and there will be a mass attached to one end of the string. It has to move in a vertical circular motion, which means against the gravitational field. If that was the case, with what velocity I should actually push it so that it makes the complete revolution. Okay, so that's what I need to find over here, and what will be the energy stored at every different instant in that particular circular motion. That too is something that I'll determine, right? We will see that experiment. So here you have got a string. One end of a string is actually fixed, okay, which means it is hinged. So that is fixed, right? So on the other end you have got a mass which is hanging. Okay, so you have got a bob, right? So this pendulum like structure is going to spin in a vertical circular motion. Okay, so it is going to complete one complete circular motion against the force of gravity, right? This is not an horizontal circular motion, so in this case it is like a vertical circular motion. So that's what it's going to happen here. So this is just a simple pendulum. That's it, finished. Okay, so you have I have just chosen like three different positions, which is like A, B, and C at three different instances. So we will find like what will be the energy at these three instant. One will be the bottommost point, and the other one will be the topmost point, and the other one will be the center one, like a intermediary one. Same way, even at different whatever point they're asking us, we will be able to find the energy stored in that particular bob. That too could be actually easily determined. Okay, right? Fine. Okay, so here let me tell you all those parameters that I've written you over here. Okay, so this is like hanging. Initially when it was addressed, this was just simply hanging, and the mg will be the force that was acting downwards. Okay, so mg was a force that was acting downwards. So to balance this mg, there will obviously be the tension in the string, okay, which will act opposite to that of the mg. Okay, so when the bob is at rest, so that's the first statement that I have written over here. So when the bob is at rest, obviously tension in the string will be acting upwards, mg will be downwards. It is at rest, which means the net effect on the left hand side, on the right hand side is going to be zero, right? So that's how we do the force balance, right? So if I do the force balance when the bob was at rest, it will be like T upwards minus mg, that will be like downwards, which should be equal to 0 because there wasn't any motion that was observed in that particular bob. Okay, string is considered to be massless, do not want to worry about the string. Okay, so here obviously when the string was at rest, T will be equal to mg. So the tension in the string will be good enough to balance this mg. If the tension in the string was less than that, then obviously this will fall down. The string will cut and then the bob will fall down, right? Okay, so then what I'm going to do is I'm just going to give a push to it, right? So the push is good enough so that it is able to make one complete revolution. Okay, so if the velocity with which I'm going to push this one is, if it was less than this velocity va, then what will happen is it will just go up to certain limit. It will not be able to make a complete revolution, and then it will just fall apart, and then it will just fall down. Okay, so that will happen. So that shouldn't be the case here. The velocity should be good enough to make that particular one complete circular motion. Okay, if it was greater than that optimal velocity, then it is of no issue. Still it will be able to make that revolution, but it the velocity should be optimal so that it is able to make that one complete revolution. Okay, so that's the hint with which I'm just going to solve this entire sum. Okay, so the velocity is optimal, is the minimal velocity with which I need to push it so that it is able to make that one complete revolution, one complete circular motion. Okay, right. Now I have just randomly chose those 3 points. In this first point, the velocity will be tangential to that position, which will be like horizontal, and horizontal, which means towards the right, plus x direction. And when it is at point B, the velocity VB will be exactly opposite to that of the mg. So that's going to be the point B. Okay, which means it has covered vertically the distance r. Okay, so that's going to be the case. And when it is at the topmost point, in that situation, the velocity vc will be directed towards the left, which means minus x-axis. So that's how that's going to be the construction of this particular experiment, right? So those will be the different positions. Fine, got it. So now what I'm going to get is, initially, let me consider this to be the starting position, which means at this point, obviously, this was the starting position, which means obviously at this point, potential energy U should be equal to 0, right? And then when it has reached the topmost point, obviously the kinetic energy would have reduced. Whatever kinetic energy that it has lost should be stored in the form of potential energy against the force of gravity, right? Gravity is going to act downwards. Even though this is moving in a circular path, end of the day, it has covered a displacement d, right? It has covered a displacement d against the force field. Okay, whatever distance that it has covered along the horizontal direction will not be considered, because that will not amount to the energy storage, right, or the work that is going to get involved. Fine, this is something that we have already seen in the last class. Whenever you move perpendicular to the direction of the force field, then in that situation energy will not be involved. Okay, it will neither be stored nor be released. Both those stuff is not going to happen in that case. But it is pretty obvious we are just moving against the force field or against the gravitational field in the situation. Therefore obviously some part of kinetic energy would have lost. Va will be greater when compared to Vc, and that lost kinetic energy will be stored in this particular bob in terms of potential energy against this force. Okay, so when this is about to make this complete revolution, it will again gain all those kinetic, it will gain the kinetic energy from the potential energy. Again, when it reaches this bottommost point, it will end up having the same velocity Va if there wasn't any loss to the surrounding. Okay, so let me find out what will be the potential energy that could actually be stored between these 2 points. In the initial potential, the potential energy was 0, and the final potential, you did have some amount of potential energy. If the potential energy was 0 in this position, obviously change in potential will be like final potential minus the initial potential. Initial potential in and itself is 0, so I do not want to consider this stuff. Just if I just calculate the final potential energy, I'll end up getting the potential energy that got stored. Okay, it should be clear. So to get the potential energy that gets stored, what will I do is U will be equal to, simple straight away, negative, force is going to be constant, therefore I do not want to integrate things of that sort, negative of force times displacement, right? If it was like work done, then I'll not introduce this negative sign. Force times displacement will give you, I mean, let me plug in vectorially itself, vector F dot vector D. Okay, so that will get you the potential energy, right? So to get that potential energy, what I could do is, F was actually acting downwards, which will be equal to mg minus j cap, negative of mg minus j cap, okay, dot product with displacement distance d. Okay, so if I have to find the distance d, it will be the point C position, and the initial point was like point A. It has traveled in a circular path. I do not want to consider this horizontal displacement and things of that sort. Only thing that I'm worried about is the vertical displacement. Okay, so that is how I do the dot product, right? So here in this situation, obviously, if I'm about to choose this point, I'll end up getting some x component and some j component. I just need to worry about only the j component. But in this situation, I have reached the topmost point, which is in aligned with that of the point A. Therefore, I'll just only have the j component, right? So the displacement will be like r plus r, okay, that too it will be along the plus j cap. So this was the point of throw or point of push. Therefore, this will be my origin. So when you compare it with the final position, that's going to be along the plus j cap. Okay, so that will be in the positive direction. Okay, so the positive direction, what was the displacement? It was equal to r plus r, so that will be like 2r. Okay, straight away simple one. So here you will have the next one will be like 2r and then the plus j cap. Okay, so the potential energy over here will be like m. So generally when we find the potential energy, so that will be the generalized formula, which will be like mgh against the gravity. Okay, so here also we will end up getting the same thing, mgh, because mg negative sign negative, it will become positive. Therefore that will be like mg j cap. That will be the only component that will be involved here. The display horizontal, here the vertical displacement h was equal to 2r, right? So you will get the answer to be like mg 2r, mg 2r. Okay, so generally while doing the sum, how we will actually find the potential energies by using this formula straight away, which is like mgh, because negative negative sign has been tallied and then it has become positive. Height will always be considered positive. Therefore mgh, that will give you the potential energy that was stored in that particular object against the earth's gravitational field. Okay, same way here, mg and then the height h was equal to 2r. Okay, so from this it should be obvious. I could actually get into this formula by using this one. I could actually get into this result by using this formula mgh. Okay, right? Whatever it is, you should be clear with this basic idea and notion. Just plug in negative sign in front of the work done, you will end up getting the potential energy. So that will be the potential energy that actually got stored when it has reached the topmost point, which means this amount of energy, mg2r amount of energy, will be lost in the kinetic energy, which will get stored in form of potential energy into that particular object. Okay, got it? Right, you shouldn't have any doubt on this stuff. It should be simple and easy. Then what you have got is actually, when a bob is in circular motion at point A. Okay, so at point A, I'm just going to calculate. I'll do the force balance, and then what will I do is then I'll find the energy, total energy at that particular instant. Okay, so total energy will be designated by capital E. Okay, so if you find a symbol like capital E, in majority of the situation, that will represent total energy. Sometimes in 12th grade we'll consider this to be like E as an electric field. Okay, so it depends. As far as 11th is concerned, whenever you see the notation E, it simply means total energy. Okay, or else they would specify it clearly. Fine. So at point A, at position A, I just gave horizontal push to it, and it received velocity of VA. Okay, so that was the velocity that it got received. Fine. So if it has to move in a circular path, obviously you need to have a centripetal force involved in it, right? So here at that instant, I'm going to freeze it. I just gave a push to this bob such that it is able to make that one particular complete revolution. So that should be the case. If that was the case, okay, if that was the case, I'm just going to do the force balance, right? If I have to do the force balance, tension in the string is acting upwards, mg is downwards, right? Then when these two stuff is going to balance, obviously the bob will be at rest. But in this situation, it is having an horizontal velocity. Same way, someone is pulling inwards by some extra force other than this of mg, so that I'm able to move in a circular path. Okay, so that extra pull will be given by the tension in the string. Fine. If I do the force balance stuff, you will get it. So only two component that is involving over here is like T and then the mg. So T will be acting upwards. Same way mg will be acting downwards, right? Fine. So here you will have like T that will act upwards. So here you will have like T which will act upwards minus mg that will act actually downwards, which will be equal to not zero in the situation, because you will have, this will end up generating the centripetal acceleration. Okay, so if T and mg was balanced, then the bob will be at rest. So then in that situation it was at rest. If it has to move in a circular path, tension in the string should be greater than that of the rest condition, because that is when you will end up having that extra centripetal force which will be responsible for the circular motion. Okay, so obviously when you do subtract these two, t minus mg, right hand side is not going to be 0 because you had certain acceleration into it which was like ma centripetal. Okay, yeah. Okay, ma centripetal. From the experiment, it should be obvious. It is moving in a circular path. Therefore, you should have an acceleration into it. That's obvious, right? Ma centripetal. Fine. So now just let me do a rearrangement into it. So the next step will be like t minus mg. That will be equal to m. What was the what was the equation for a centripetal? A centripetal will be equal to v square divided by r. Okay, so that's the extra amount of tension that it needs to give. M v square va square divided by r, because at that instant the velocity was equal to v subscript a va square divided by r. Okay, now let me do the little bit of rearrangement thing. So we will have like t which will be equal to mg plus m v a square divided by r. So that will give you the tension of the string at that particular instant. So that will be greater than that of the mg plus m ba square by r. So some extra term will get added to this mg. So that is when that extra component will be responsible for the circular motion of that bob. Okay, right. So next what I'm going to do is I'm just going to get the total energy at that particular instant. Okay, so the total energy at that point A will be equal to one and only kinetic energy. Therefore you will have half m, okay, v a square plus 0, because you do not have any potential energy generated because that was the point of push. Okay, got it. So now let me give you one more condition into it, okay, which I've already told you, but I'm just going to elaborate on that condition. Okay, so here what you have actually got is you've got a point from which I'm going to push it with the exact optimum velocity. Okay, if that was the case, then it will be able to make that complete revolution. Okay, if the velocity was less than that, then obviously it will just go to one part of the circle and then it will just fell down from that point. Okay, so it will just be able to make some arc and then it will just fell down and then it will just fall down and it will end up having an oscillation. Okay, so that shouldn't be the case. It should do the complete vertical loop. Okay, so with what minimum velocity I should push so that the velocity at this point is good enough to complete the revolution. Okay, if the velocity at this point was greater than that one, then what will happen? Then obviously if the velocity vc is like extra, in that situation the tension in the string would have, you would have some tension in the string, which means the string would have been stretched. Okay, because if I'm just going to cut at this instant, then what will happen is this will fly off. Therefore that you need to have some tension so that I'm able to balance and I'm able to do that complete revolution. Okay, so here this is a kind of this is the kind of that special optimal situation where you do not want to have any tension in the string. That mg should be good enough to balance this mass so that it is able to make this revolution. Okay, if the mg is going to dominate at other instant, then it will just fall down from that point. Okay, which simply means I didn't give enough velocity at the point of push. If I just gave enough velocity at the point of push, then it will come to the topmost point where this mg in and itself will be good enough and it will act as a centripetal force so that I'm able to complete this circular loop. Okay, you got it right. So this point, at this position, there wouldn't be any tension in this string, which means T in this string will be 0. This is a special condition. Okay, if the velocity was greater than this VA, then obviously the velocity VC will be greater. If that was the case, compared to this velocity, you will have like much more velocity. If that was the case, then I need to pull this inwards. Okay, this inward pull given by the mg wouldn't be good enough. Then you will have tension in the string. Okay, if tension in the string was exactly equal to 0 and mg in and itself is good enough to make the turn, then obviously I have given the optimal velocity. Okay, if the velocity was less than that of this optimal velocity, then it will just make certain arc and then it will just fall down from that particular position. Okay, so that too shouldn't happen. It has to make that exact circular motion without me giving any extra push to it. Okay, so that should be the case. Okay, Got it? Then in that particular, if that's the special case, then obviously tension in the string will go to 0 when it has reached the topmost position. So that point is, so we could actually tell that point position is like string got slackened. Okay, string got slackened, which means you do not have any tension in it. Slackened. Okay, it was loose. Okay, there wasn't any tension involved because of that circular motion, so that's going to be the case. Okay, so at topmost point, if mg in itself is good enough to give that particular object, if mg in itself is good enough to give that particular object centripetal force, then tension in the string wouldn't be needed. Okay, so that's the situation that I'm going to consider over here. Okay, if the velocity was greater than this one, then obviously at the topmost point you will still have tension in that string, which means string will not get slackened. Okay, if the velocity that I've given at the bottommost point is less than this one, then obviously it will not even make that complete circular motion. Okay, so you should be clear with that logic and idea that I'm telling you. Okay, got it? You shouldn't have any doubt. So here it should be clear, mg is the only force that is acting, which is in and itself is good enough to make that circular motion. Okay, so next we will see, like at point C, what is going to happen. From that I'll be able to get the velocity at VC, from which I'll find rest all other velocity. Okay, so here purposefully I've left this VA. I'll find it after finding the velocity at point C. Okay, so that will be in the next page. So in the next page you have got like at point C. So at point C, let me do the force balance. You do not have the tension in the string. Okay, so that's going to be like 0. So only component that will be involved is like the negative minus mg, which will be equal to m. Okay, a centripetal, right? So how will I be able to write the a centripetal? So that will be like bc square divided by capital R. Okay, so negative mg will be equal to vc square divided by capital R. So how is this acceleration that is acting in this particular object? Obviously centripetal acceleration is also acting inwards, right? So in the situation, centripetal acceleration was actually upwards, therefore I ended up solving it. Okay, t minus mg, which will be equal to the ma centripetal. So a centripetal was acting upwards. Fine. So in the a centripetal will always be directed towards the center. So in the situation, it was acting upwards, which was j cap. In the topmost point, that a centripetal was actually acting downwards towards the origin. Therefore, you will have like one more negative sign into it, minus mg, because that too is acting downwards. Same way centripetal is also acting downwards. Therefore, you will have like negative j cap into it. Okay, whatever it is. Now let me solve it, and I'll end up getting the v centripetal. Right, now let me do the solving stuff. M will get cancelled out. Okay, negative and negative, that will become positive. If I just do the rearrangement, I'll end up getting the answer. Right, so you will have vc square, that will be equal to root gr, right? That will be equal to g times r. Okay, so vc will be equal to root gr. So that's the velocity that is needed over here. Okay, so whatever the mass it is, it doesn't actually depend on the mass, because the mass will get cancelled out. Fine. So proportionally, if the mass was heavier, proportionally the force that is going to act will also be heavier. So that's not a problem. Only thing that we are worried about is the acceleration component. Okay, so here in this case, when this object that I'm going to push is going to reach the topmost position, which is like VC, with a velocity that is equal to root gr. If that was a velocity that it has, that this particular mass has, then obviously it will be able to make this center, it will be able to make this circular motion. Okay, if this velocity was less than this, then what will happen is it will not even reach this point, it will not even make into this point, it will just reach somewhere in between, and then it will just fall down. Okay, so the velocity that I gave initially wasn't good enough. If the velocity was greater than this one, then obviously this mg isn't good enough to pull this one in so that it will be able to make a circular motion. Therefore the string will not get slackened. What will happen is the string will get tightened, which means it will have some amount of tension acting, some amount of extra tension that is getting produced. initially the tension was greater. As it keeps on moving in the circular path, the tension will reduce, and then finally the tension will reach its minimum. In this situation, the minimum was equal to 0 if the velocity was equal to root g by root g r. If the velocity was greater than this one, then obviously the tension will decrease and it will reach certain minimum value when it has reached the topmost point, but it will not be equal to 0 because the velocity was greater than this optimal velocity, which was like root g r. Okay, if the velocity of that particular object when it is about to reach the topmost point is going to be like root gr, then we will be able to make that complete turn. Okay, for example, you can consider a roller coaster that is going to move in a circular path. Okay, so if it has to make a complete vertical circular loop, then the velocity at the topmost point has to be minimum equal to that of root gr. Okay, so anyway you will have like other safety measures and other stuff into it. The point is it should be greater than root gr. That is when it will be able to make this vertical, I mean that vertical circular motion. If it was less than that, then it will not be able to even make it into the topmost position. Okay, so it will just come, it will just fall back from that intermediary position itself. Fine. So in the case of roller coaster, this should be the minimum velocity that is needed, right? If it was greater than that velocity, obviously the velocity will be greater than this root gr. Okay, because if it was greater than that velocity, then that rail will give you extra needed force, centripetal force, so that we'll be able to make that particular circular motion. Okay, in this situation you do not have any external rail. Here in this situation, that extra tension will be given by the tension in the string itself. Fine, so it should be clear. At the bottom point the tension will be maximum. As it starts moving upwards, the tension will decrease and then it will reach the minimum at its highest point. Okay, so that's the notion. So this is the starting condition. So this is the starting velocity with which it could make that full revolution. Therefore, when it has reached the topmost point, the velocity became 0, right? So that's the notion that you need to know. Fine. Anyway, we have got the velocity, minimum velocity with which it should reach the topmost point has been found out. From this, I'll be able to get the total energy of things of that sort, right? So to get the total energy, what I could do is I've got here the velocity at the point C, right? So to get the kinetic energy, it will be equal to half m Vc square will give me the kinetic energy. What will be the potential energy at this point? So the potential energy at this point will be mg2r, right? If I do add these two stuff, kinetic plus potential, you do not have any other energy loss in this case, right? Light or sound energy, whatever it is, you do not have any other energy loss. Therefore, kinetic plus potential will give you the total energy, right? So obviously here the total energy at the point of push was equal to half mva square. So total energy will always be conserved, right? It is not going to change. Therefore, I'll be able to substitute the total energy over here from which I could actually solve it, right? So first let me do it for the point C, then I'll do it for the point A. Okay, so for the point C, if I do solve this one, you will have E, which will be equal to half m. Okay, so half m vc square. So that's going to be the kinetic plus the complete potential energy that got stored, which I have already found out, right? So that will be equal to mg2r. Okay, so here if I do replace this one, you'll have like half m, instead of vc square I'll substitute like root gr the whole square. That's going to be mgr plus mg2r. Fine, if I do add those two things, I'll end up getting the answer. So if I add, what will I get? mgr, it is like same. Here you have got like 2, so that will become like 4. So 4 plus 1 will be like 5. So that will be like 5 by 2 mgr. So you'll end up getting 5 by 2 mgr, right? This one should be clear, right? You shouldn't have any doubt. So now I have got the total energy, which is like 5 by 2 mgr. If I substitute this total energy, so in whatever position it is, this 5 by 2 mgr is not going to change. Got it? So here if I substitute like E for the point A, E, I'll be able to substitute like 5 by 2 mgr. Okay, so that will be equal to half m va square, right? So here m will get cancelled out, half will get cancelled out. So he will have, so the minimum velocity with which I should push this one will be equal to root of 5gr. right? So that should be equal to root of phi gr. This should be the minimum velocity with which I should actually push this bow. Okay, so if I push this bow with the velocity of root phi gr, then automatically it is moving against the gravitational field. Therefore, it will slowly lose its kinetic energy, and when it reaches its topmost position, it will have the velocity to be like root phi gr along the negative x-axis. Okay, so this root gr, if it has this velocity root gr, then mg in and itself will be sufficient to make the circular motion. Okay, you do not want any extra tension to get involved. If it was greater than this one, then obviously tension will be involved. Okay, so that's the idea that you need to know. Got it? So now I have found out like va, which was equal to root phi gr. Then let me do it for the point b. Okay, so the point b will be the intermediary position. So I have chosen that point such that it is in the half semicircle of that motion. Okay, so it is exactly in the half of that motion, which means it is like parallel, I mean, or it is like horizontal to the origin, something of that sort. Okay, so if that was the case, then what will be the parameter that will get involved? You will have like mg h, which will be equal to this distance, because h should always be the distance that it got covered against the gravitational field. Okay, so that will be this r, and then you will have the velocity to be like vb, right? So let me do it. It's easy, simple, straight away. So the total energy E will be equal to half m vb square. Got it? Kinetic energy, that vb is something that I need to find. Okay, so plus the potential energy. So potential energy is just the half, that the radius is just the radius that it has covered, right? So in the previous case it was like 2r for the complete circle. Here it is like a semicircle stuff. Therefore you will have mgr. Okay, so E equals half m vb square plus mgr. Now instead of E, I'll be able to substitute 5 by 2 mgr. So you will have 5 by 2 mgr, which will be equal to half m vb square plus mgr. Okay, now let me do the cancelling stuff. You'll get the answer. M will get cancelled out, and then if I do the rearrangement, you will have, if I do the rearrangement, you'll get the answer straight away, right? So you will have something like this: 5 by 2 gr minus gr, which will be equal to vb square. Okay, fine. So 5 by 2 gr minus gr will give you like 3 gr. That's going to be like root 3 gr. So you'll have vb, which will be equal to root of 3, which will be equal to root of 3 gr. Okay, so these are the three different positions that I have chosen you. Okay, so even I'll be able to get for any other arbitrary position. Next, let me choose any other random position in the circular motion. Okay, so on that particular point, I'm just going to get the velocity of that mass. Okay, so to get that one, you do the same thing again. So to get that one, I'll consider the total energy to be like 5 by 2 mgr, right? So in this entire sum, in this entire stuff, it should be clear. The total energy will be equal to 5 by 2 mgr only if the velocity at the topmost point is equal to root g by r, root gr, which means the string should get slackened when it has reached the topmost position. There shouldn't be any tension in the string. Okay, t should be equal to 0. If that was the case, that is when E will be equal to 5 by 2 mgr. Okay, or else the total energy will be something greater than that one. Okay, got it? So here that's the case. When it has reached the topmost position, tension was equal to 0. Therefore 5 by 2 mgr is the total energy, which will be equal to half m vd square. So this is the point where I need to find the velocity. Okay, so half m vd square plus the potential energy that I need to substitute over here. Okay, this position is like in the second quarter of the circle. Okay, so it started from the origin, from, I mean, the mass started from this position. I consider it to be the origin. Okay, so here this distance was equal to the r, so that was a point B. So it has completed the first quarter. So here the mass is between the second quarter of the circle. Okay, so here it is, the point is like position D. Got it? So when it has reached this position D, let me put it this way: the vertical distance was equal to r by 2, right? So once you get this vertical distance, whatever it is, r by 2, r by 4, r by 3, whatever they give you, from that I'll be able to do the solving to get the velocity at that particular position. Okay, so here half mvd square plus, and the other one will be like the potential energy, that will be equal to mg. So that will be equal to mg and then r plus r by 2, right? R plus r by 2. Got it? So now m will get cancelled out, right? So all those m will get cancelled out. M will get cancelled out. So only stuff that will be left is like 5 by 2 gr, which will be equal to half vd square, and then plus you will end up having 3 gr by 2. Okay, so 2 will also get cancelled out. 2 2 2. So we just have like 5gr minus 3gr, that will give you like 2gr. So vd square will be equal to 2gr. Therefore vd will be equal to root of 2gr. So that will give you the velocity of that particular position D, point D. Fine. So from this, it should be clear whatever position they are asking you to find, we will still be able to get the velocity of that particular bob. Okay, so you should be clear with this experiment that we have done over here. So it's a kind of vertical circular motion of a bob, right? You shouldn't have any doubt in the experiment that I have done over here. It should be clear, and you should be clear with all those derivation part that I have done, right? By the way, you should also know the basic understanding behind the total energy and then the potential energy, right? So these three stuff we did see in this class. In the next session, we will do like what is meant by power and all those stuff. Same way we will do like spring. Okay, so how does the energy get stored in the spring in the form of potential and then the kinetic energy. Okay, some basic part regarding the spring will be done in the later chapters, which means in the oscillation chapter we will do more exhaustively related to the spring. As if now we will see like how does the energy get stored in the spring and all those stuff in the next session. Okay, so with this the video gets completed. Bye.